Hi everyone. In the last video I compared the performance of CUDA on the GPU against OpenCL on the CPU on the Jetson Nvidia Nano DevKit in the context of the OpenCV sample application that I have been using that does a time exposure algorithm based on frames that are captured from the camera. In addition to capturing and doing the time exposure, the application does a little bit more work, which involves calling some OpenCV functions to calculate the discrete Fourier transform on the on images, and then displays the images and their DFT using OpenCL, and I also use IMGUI for some of the GUI controls for this application. So as I saw in the last video, CUDA was not performing for me as well as OpenCL on the CPU on the Jetson Nano DevKit, but I attributed that to my CUDA implementation being a naive, rough, early implementation, that maybe some tweaking would help improve that. And so I tried a few different things, and I wanted to share that in this video with the results of those tweaks. What I've done is I've added some checkboxes to the application so that I can try different CUDA tweaks on a live capture, so I don't have to keep starting and stopping the application. In any case, I'm going to switch to the Jetson Nano and share the rest from there with you. So if I launch the program, what you'll see is, as usual, it comes up, and right now it's capturing the frames using OpenCL. The CUDA device is the Nvidia Tegra X1, so that's the GPU which is a architecture capability 5.3. It's a Maxwell architecture. It has one multiprocessor in it with 128 cores, and as normal, each warp on CUDA devices is 32. So there we have 4 warps per that multiprocessor. The maximum number of threads per block on this and most CUDA devices is 1024. Since this the maximum number of threads per multiprocessor is 2048. Now the grid dimensions here are different, and I'm going to highlight this. This launch configuration is different than last time. Last time I was running with 128 thread blocks, and when I analyzed my data that I'm working on, I realized that maybe this might be a better launch configuration. Basically what I have is 307,200 pixels. That's 640 by 480. 640 columns, as you can see here, 640 columns in this direction, 480 columns in this direction, 480 rows in this direction. That gives me 307,200 pixels. So I chose, and this was the same last time, 1024 as the block dimension. That is how many threads are in each block. So it's that I set to the max threads per block, and previously I was using 128, which would have been the number of cores, but I decided to basically take the 307,200 pixels divided by this number, and then choose that as my number of thread blocks. So my grid dimension in the x direction is 300, and my block dimension is 1024. That gives me a grid size that is exactly equal to the number of pixels that I have. Now, in the last video, I was using a CUDA kernel that had was using a grid stride, so it would stride. So each instance of the CUDA kernel would work on multiple pixels. And one of the things I'm going to compare is using grid stride kernels versus non-grid stride. So if I have each kernel that instance work on 1 pixel, then I would get 307,200 kernels launched. But if I use grid stride and do a grid stride factor of 3 and let each instance of a kernel work on 3 pixels, then I can reduce the grid configuration, launch configuration, to 100 blocks with the same number of threads per block. So basically, my it would still produce. It'll still work on all the pixels, but it would take 1/3 the number of kernels, and as a result, the grid stride would be 102,400. So each pixel, each kernel instance would work on, let's say the first one would work on pixel 0, then it would stride across the grid to the next one, and then again another 102,400. So, and then that should be all the work that each instance of the kernel will do. Based on these numbers, my occupancy, GPU occupancy is 1. So I have good occupancy based on the numbers that I chose. And I have added checkboxes to the CUDA options so that I can turn grid stride on and off on the fly, and we can see the impact. But basically, what we're seeing now, right now, I'm running with OpenCL. This is running OpenCL with the with this device. This the OpenCL device is implemented using the pthread library on the CPU, and it's using the Cortex A57 CPUs that are in the Nvidia Jetson Nano. In any case, as you can see, this is the column that I'll be monitoring. This column shows that the time it takes to compute the time exposure algorithm on each on 100 frames. So I capture 100 frames. It takes me 10 seconds to capture those 100 frames. So the frames per second rate is 10. That's the target frames per second that I want to keep. And for this particular application, that's what I'm targeting. So I don't want to drop below 10, and I really don't want to go above 10. My 10 is what I need for this algorithm, and that's my target. But in any case, this 274 milliseconds that it takes to perform the time exposure algorithm is the time it takes to do so on 100 frames. So every line, basically another 100 frames is captured and computed. So this is the total time that it took for this the captured 100 captured frames. So 273 right now is the time that it takes OpenCL on the CPU. For example, the numbers for OpenCL are showing up around 274. This is 254 is the lowest so far, And since I've been capturing for a while, it is yeah, it seems like it's under 300. I saw maybe one 300 millisecond number in there. In any case, since this has been running for a bit, I'm going to actually stop, because what happens is I will restart it and then capture a few OpenCL measurements. But since I've been talking, this is actually getting close to 6,000 frames. At 6,000, I have captured enough frames, 6,000 frames for a full 10-minute of time exposure. So then at that point, I don't have to allocate any more memory. So there's a little bit of a performance, the time that it would take to allocate memory for each captured frame is no longer there as part of the calculation. There is about 1,000 frames left before I hit that number, so it's too close. I'm going to start all over again so I can do the this comparison with OpenCL with that overhead in the picture. So just running it one more time. I've restarted it, and again, I'm going to let it capture some more OpenCL numbers so that we have a reference. But now I have about 10 minutes left before the overhead for grayscale allocation, buffer allocation for the grayscale frames goes away. So I can do the measurement, do the comparison in that time and get an apple-to-apple comparison. This basically what's happening right now is about 200 and again under 300 for OpenCL. So I'm going to switch to CUDA. Again, looking at this column, I'm going to switch to CUDA, and the selection I have is I'm not using pinned memory, I'm not using unified memory. I am using a grid stride kernel. This is the situation that I had in the past video. And with CUDA running with that launch configuration, I am seeing about 350 milliseconds. So that's clearly less, more time for CUDA on the GPU than it was taking OpenCL on the CPU. OpenCL really was under 300, whereas CUDA using device memory is more expensive. One of the tweaks that I tried was switching to pinned memory. Now, there's this article that describes using pinned memory. It's called How to Optimize Data Transfers in CUDA C++. It's on the Nvidia developer blog. I'll put the link on this in the video description. But as you can see, this is basically describing how, if we use pinned memory, then the CUDA drivers don't have to copy the data from a pageable memory to a pinned memory before copying it to the device. The idea is if you allocate pinned memory, then there's one less copy. So I tried that. In the context of my application, that did not really give me anything. Actually, it was not as good as just device memory. So if I switch to that, let me go back to the screen. So if I've switched the checkbox to pinned, and I switched it around here. That was the last measurement for device memory. So as you can see, when I switched to the pinned memory, the price went higher. I mean, it's taking longer. It kind of makes sense again on the Nvidia Jetson Nano. The device doesn't have onboard DRAM, any DRAM on board. it shares the 4 gigabytes of RAM that are available on this platform with the CPU. So I'm not sure. And in any case, the data has to be copied to that pin memory from CPU memory. So there's a lot more overhead. So that clearly was not a good choice for me. But one difference between pin memory and device memory is when I use pin memory, I use I call CUDA memcopy async. So I was hoping that that asynchronous nature of the transfer would help, but that didn't in this particular application for this application. So my next option is I've added the checkbox is to use unified memory. And let me start first without capturing into uniform memory. Basically, what happens is here is when I switched. These are numbers for pinned memory in the 500 range. Here's when I switched. So this is really the first unified memory measurement. So it's a lot less than pinned memory, and it seems like not much better, or maybe similar to device memory. Maybe better than device memory too, but certainly not as good as OpenCL. So there's still not enough. One thing that happens here is when I select a unified memory, I'm going to make one call to CUDA malloc managed and grab enough memory to handle for the device to have enough a buffer for this grayscale image. I'm sorry, color image, plus a buffer for the grayscale version of that, and plus another buffer for the time exposure. So those three buffers come from a single call to CUDA memory, CUDA malloc managed. I break it up into three different buffers, and I don't make three different calls to allocate three different buffers. Somewhere in one of the articles, I read that this was a better technique to coalesce all these calls, all these allocations into a single call, if possible. So that's what I'm doing. With using CUDA unified memory, one of the things that I can do is, well, the color image has to go from a CPU memory to the CUDA unified memory so that the CUDA kernels can work on them. Once the CUDA kernels have finished their task, what they do is they produce two new images, and those are sitting in two CUDA buffers on the device. Those have to be brought up back to the CPU. One is a grayscale image that is used to calculate the DFT you see on the right. And then the other one is the time exposure image, which is calculated on 10 minutes worth of grayscale images. The grayscale image, other than calculating the DFT, it's not used for visualization, and it goes on a list, on a queue, and then 10 minutes later it gets deducted from the pixels of it get deducted from the time exposure, and a new frame is added. So that's how the algorithm does the time exposure. However, the time exposure image is not only used to calculate this left side DFT, but it's also fed into OpenCL to using a texture, OpenCL texture, to draw this image on the screen. The buffer for this time exposure doesn't change. It's the same buffer all over and over again. On the GPU, the buffer for the grayscale image doesn't change either, but when it's brought up to the CPU, there is a different target for that for every frame for the first 6,000 of them. After that, these buffers are recycled. The 6,000 grayscale images are recycled, so there's no allocations, but the target of the copy is different. So one optimization that I was able to do was to not call CUDA memcopy from the device explicitly on the time exposure and let the unified memory do its thing. That when I start using that time exposure buffer to calculate the DFT, the CUDA libraries, the driver will bring the pages up, will bring the bytes up from the device into CPU memory. So I was able to eliminate one call to CUDA memcopy. I have two calls, one for the grayscale, which goes to different buffers on every frame, and then one for the time exposure, which always goes to the same CPU memory. So by doing so, by using the actual unified memory for the time exposure, I'm able to eliminate a CUDA memcopy. Now that's one of the tweaks, and that's why right now we're seeing 300 and something like that in the 350 and above. So the next tweak that I can do is tell OpenCV to actually copy the camera image directly into the unified frame, the CUDA unified frame. And that is a savings, because then I don't have to copy it first into a CPU frame buffer and then copy it to the CUDA unified. I directly have OpenCV do that by clicking this checkbox. Now here's when I clicked it, and I'm expecting to see some gains, and I do. Immediately I see it dropped in the low 300s, and it's actually even I'm expecting it to do better. Yeah, it's going to the 240. So if I ignore this line, usually during that transition, when I click one of these checkboxes, there's some data movement that has to take place to make sure the CPU is synchronized with the GPU and the buffers are up to date on both sides. But clearly, this is definitely giving me the best results with CUDA right now. Is starting with this, I'm seeing now numbers in the 200 millisecond range, which is similar to what OpenCL on the CPU can do. And that closes the gap that I was having between CUDA on the GPU versus OpenCL on the CPU. I'm hoping there will be more tweaks that I can make, and even make it better in favor of a CUDA GPU, because if I want to move my application to this platform, it makes sense for me to do that only if I'm going to do it in CUDA. Otherwise, what's the point of and so I'm looking for ways that I can optimize my code, and so far using unified memory allows me to do one less copy, and then also capturing directly into the unified frame buffer. Then that's another savings, and now the gap is closed with OpenCL. OpenCL was in the 200 something range, and now I have good numbers with CUDA. So one more option I have is to use a grid stride kernel or not. At the moment, so far I've been using grid stride kernels, but somewhere I read in one of the articles that perhaps using grid stride kernels yeah, I'm going to switch to the article so that I can share that with you. So this is the article. These are older articles. They're from 2013. So I don't know how relevant they are on these newer platforms. But this is titled "How to Access Global Memory Efficiently in CUDA C++ Kernels." But here in this sentence here, it said for strided global memory access, we have a different picture. For large strides, the effective bandwidth is poor, regardless of architecture version. This gave me the hint that maybe, okay, maybe I should try non-strided kernels. Basically, each kernel will work on one pixel. So I added the checkbox so that I can. Currently, I'm running I'm getting these numbers with a grid stride kernel. So each kernel instance is actually computing three pixels. So the first one, for example, will calculate the first pixel here and jump that 102,400, I think, here, and then another 102,400, and then that's this. That by doing so, it's able to do 3 pixels per invocation. And I'm going to switch to a kernel that doesn't use grid stride. So each kernel instance that is invoked, launched, will be working on a single pixel. So let's see what that does. So I switched around here, and I don't know. Well, look at that. It's like the first number. I usually don't take this first number into account. I usually wait for a few more lines and kind of see what the differences are, what the numbers are. But I think the result here is I'm not clear which way it goes. Yeah, it's inconclusive for me. Sometimes it's higher, sometimes it's lower. So I'm still debating on this. However, I want to point out one thing about capturing into the capturing from the camera directly into the CUDA unified frame buffer. That doesn't work on every platform. It works on the Nvidia Jetson Nano. It gives me an advantage. And it also works on Ubuntu desktop using a GTX 950. If I boot the same desktop into Windows and capture it directly into the frame, unified frame, I get worse results. So it really depends on the OS, on the hardware, on everything. So having these checkboxes lets me run this program on different platforms and see which one's best. But it looks like I don't know. It looks like it's hard to tell whether grid stride helps or not. But in any case, the margin between CUDA and OpenCL has closed. Virtually, they're performing the same. But again, I hoped more. I hope to do better with the CUDA on this GPU. So the big price I'm paying is for moving this data, and the efficiencies that I have to find is by understanding what my data looks like and what are the best strategies. I have to also look into making sure that I consider how the impact on cache lines are and how the impact on all sorts of data movements are. So for now, this is about as far as I've been able to bring it and improve my implementation in CUDA so that at least I don't have such a big gap, and then find out what are some of the tweaks that I can make. I hope this was useful, and it's definitely been useful for me to be able to get to know my data better and the data that I'm working on better, and to also know the data movements, where what needs to move, where and how the memory access patterns are. So that's basically where I may be able to gain more. And if I come across with some other tweaks that I can make and share it, I'd be happy to do that. But for now, I think I'll just leave it at that, and see you in the next video. Take care.